Okay. What is a parametric equation? So you already know about functions, like y equals f of x is a function, and you know how to graph functions if you need to. Fine. What if instead of just two variables, x and y, we injected a third variable? Well, why would we need to do that? Like who cares about a third variable? So I want to give you the motivation on why you want to do this, and then we'll do it. Okay, so this isn't really in your course reader. This is just Professor Rasky here doing some philosophy. Okay, so let's say you had, y equals f of x, just say. And let's say it was like an upside down parabola and it represented the motion of a football, just say. So let's say the person, is 6 feet tall. So this represents 6 feet. And they throw the football and, up, 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 and then, crashes onto the ground. Fine. Now, in your pre-calc class or algebra class, you probably had a problem like this where they even asked you to get maximum height. You might have even had it in your Calc 1 class. And if you found the max here of this downward facing parabola, and then you used your knowledge, you got your x coordinate here after finding the derivative, you set the derivative equal to 0. And then you can get your max height here of the football. All right, fine. So what? Well, what if we want to, I claim there's something missing to this story. Well, what's the big deal? Here's the football starts here at the coordinates 0, 6, and it goes up, hits some maximum height, and lands way out here. This is what we call the range of the football. Maybe it's like 300 feet away from where he threw it. I don't know. Yeah, that's probably a little bit too much, but whatever. Let's say it is 300 feet. Hey, touchdown. There is something missing from this story. And I claim what's missing from this story is, what about time? What about it? It's missing from this whole picture. Like, let's say that the football is released here at time t equals 0. That's right when the ball's released. Fine, the quarterback throws it. And then what? Like what time is it when it achieves maximum height? Like how many seconds have to go by before it gets to maximum height? And then further, what about when it finally hits the ground? Let's say, the receiver didn't catch it and hits the ground instead of making it into the receiver's arms. Fine. How long did it take till it hit the ground? So that's a missing variable, time. So what parametric equations do, which is kind of cool beans, it's going to throw in this third variable, we'll call it t, and it could represent time. Usually we do actually have it represent time, but it could represent any other types of things. It's just the third variable into the conversation to give the story more information, because that's a piece of information missing from the story. Okay, fine. So now that you see where the motivation may come from, let's get to the beginning here. All right, so you already know how to define a function in terms of x and y. That's called rectangular form. So if you have a third variable introduced into the conversation, that third variable has a name. They usually call it the parameter. So know this vocabulary. So here's the official definition of parametric equations, and it's a lot of words, but after you see some graphs, you'll get it. So what you're going to have is you're going to have two different functions of time t on an interval. Then the function x equals f of t and y equals g of t together create a set called parametric equations, and t is called the parameter. Now, when you're trying to sketch by hand a set of parametric equations, it can be pretty slow. Why? Because your chart isn't just going to have a column for x and y only. It's going to have a chart for that parameter, t. And then you have to fill in your times and then the corresponding x and y. And then to plot it, you'll plot the xy ordered pair. So we're going to do one of these by hand, and that's the only one I want to ever do by hand for the rest of the semester. Like, don't make me do that ever again, because it's tedious. I like to use my graphing calculator. But if your graphing calculator's batteries dies, you still can do this by hand. That's the point. Okay, so what you're going to do when you sketch it by hand is you plot your points, and then each point that you have actually has an extra piece of information associated with it, what time it is. That's kind of cool. Now, when you plot all your points with increasing values of the parameter t, the curve gets sort of traced out in a specific direction, and that's called the orientation of the curve. Now, folks, all of this stuff, you're going to see it in Calc 3 a lot. If you don't have to take Calc 3 because your major doesn't require it, then all apologies to you that you are learning this sort of extra piece of info tacked on to the back of Calc 2, and who cares? Like if you're going to go to med school, I think there's at least 1 or 2 students in the class that don't care about Calc 3. They're going to go to med school, but you have to take the MCATs. Good news, the MCATs only require Calc 1 and Calc 2. They don't require Calc 3. Okay. So let's plot this set of parametric equations by hand for time going between 0 and 5 seconds. Okay. Now, normally you'll have time go negative also. Really? We could go backwards in time? Yeah, you can. So how do we fill out the rest of this chart? It's easy. Easier than finding radius and interval of convergence. So what of it? Well, if time is 0 seconds, when you plug t equals 0 into your x parametric equation, 10 minus 0 is just 10. And y is equal to 2t, so 2 times 0 is 0. So this point that you're going to plot is the point 10, 0, which is right there. So I'll plot that first and move on. Then the next time is 1 second. And at 1 second, the x is 10 minus 1, which is 9. Y is 2 times 1, which is 2. So we're going to plot the point 9, 2. And that's roughly right there. Yeah. And then I'm just going to fill in the rest of this one. Time t is 2. 10 minus 2 squared is 6. Y is equal to 2 times 2, which is 4. You want to plot the point 6, 4. So 6 is like right about there, roughly there. Fine. 3, 10 minus 3 squared. Okay, that's 10 minus 9, which is 1. 2 times 1 is 2. So we'll plot the point. Oh, hang on a minute. That's not right. 2 times 3 is 6. I don't know what I'm doing. So we're going to plot the point 1, 6. So 1, I don't know, roughly here. I'm kind of eyeballing it. Not too good there. 4, 10 minus 4 squared. Oh, we're going to get to the negatives. Okay. X is negative 6, and then 2 times 4 is 8. Plot the point, negative 6, 8. Fine. Okay, we're over here, negative 6, 8. I don't know, right about there. And 5 seconds, 10 minus 25. Ooh, boy, negative 15. 2 times 5 is 10. Negative 15 is way out here for the X coordinate, and then 10 is going to be like right there. And you connect the dots, and when you connect the dots, you have to remember the order that you plotted them. This is kind of cheesy here. It's actually a sideways parabola. And you want to put one arrow there, and that is showing the orientation. You don't need to put 57 arrows. Now, most of what we do is on MyLab Math, so you'll probably get a multiple choice. You'll get to pick which one of the graphs looks like it's the one. Use your graphing calculator. But when I do give face-to-face exams, I get some students would do this just to make sure I get it. Okay, professor, we're going in this direction. And I'm like, okay, I get the arrows. You don't have to put a whole mess of them on there. I gotcha. And that's it. Okay, I just graphed it by hand. Now, if we do this on our graphing calculator, oh, so much easier because you just punch up some buttons. So you're going to have to get into parametric mode, though. Because right now you're in funk mode. Really? I know, I don't feel like I'm in a funk. You are. Click on the mode button right there, mode. And notice I'm already in parametric mode, but you may not be. You may have this function highlighted. So you want to use your arrow buttons down to the function and then arrow to the right so that parametric is highlighted, and then click enter to actually choose it. And then hit second quit to get out of here. Okay, I'm out of here. Then hit Y equals. And now instead of the Y equals, you're going to notice that for one graph, you have to fill in two equations, an X and a Y. So here it has X1t and Y1t. And then if you wanted to graph more than one set of parametric equations at the same time, x2t, y2t, and so on. I usually only graph one set at the same time. So I'm going to clear out what I had from before. And if I read the problem, it's 10 minus t squared, and then the y is 2t. And they did ask me for time going from 0 to 5 seconds. So if I honor that, I go to the window, and for t minimum, I put 0, and t max, I put 5. And you can leave all the other settings the same. Now, when I hit graph, this graph button up here, it's going to graph pretty fast. So don't blink, because you want to be able to see the orientation that it gets sketched out. So you can see that, woo, that was really fast. So I hope you didn't miss it, but it looked like it did sketch it from right to left. And it's a sideways parabola, it looks like. Now, you could change your t minimum, although the problem specifically had time going from 0 to 5 seconds, but I can have t going negative. What if I do? Minimum of negative 5 seconds. When I graph it, check out that I get the bigger picture. Whoa! I get the entire horizontal parabola. So that's kind of cool, and that's good for you to know. Okay, any questions so far about plotting parametric mode and parametric equations? Is anybody following along with their calculator here?
Yes.
Yes.
I hope you are. It'll help you. It helps to do it when you're learning it better. Okay, so let's go back to here. Now, another thing they're going to ask you to do besides graph parametric equations, another thing they always like you to do is eliminate the parameter. Well, what do you mean? Well, look, this graph is currently represented, by x equals 10 minus t and y equals 2t, okay? So when you eliminate the parameter, you try to kill off the t. Well, how? Just erase it? Well, not quite. You want to rewrite this set of parametric equations so you get a single rectangular equation. So only x's and y's should be left, and the graph of the rectangular equation had better match your parametric curve. So the way I do it is, and I'll show you, is I write down, my two equations, and then I look at them and I go, okay, which one of these is easiest to solve for time t? Both of these are pretty easy, but I think this one, it's easy to solve for t. Why? Because you just divide both sides by 2 and you have t equals y over 2. Now what? You substitute that into the other equation for t, and you get x is equal to 10 minus, and that's supposed to be t squared, sorry, y over 2, the quantity squared. And this is a single rectangular equation that represents the graph, and which was, a sideways parabola, right? Yeah. And if you want to clean it up a little bit, x is equal to 10 minus y squared over 4. And we're done. We just eliminated the parameter. So when you eliminate the parameter, you really do eliminate the parameter. Like this graph of 10 minus y squared over 4, which is a single rectangular equation, is the same graph as the parametric equations. Okay, now we're going to do a little bit harder. What if you were given a curve that had trig in it? Sine t, cos t. So no problem. I'm going to do this with the calculator. I'm going to make sure that I'm in radians mode, because if I'm not, anytime you're stuck in degree mode, you can't graph trig because it'll show up blank. So it looks like I'm in radians mode. Okay, good. So I'll quit out of here. I'll go to y equals. Let's clear out these other equations using the clear key. And then my x equation is sine t. The y equation is cos t. And they're not telling me what's going on with the window, the time minimum. But let me just tell you, usually when you're doing trig, usually, not every time, the window is covered. Usually you only need 0 to 2 pi. And that usually gets your whole picture, usually. So If I do that and then hit graph, don't blink because we'll see the orientation. Oh, it was too fast. Bummer. Well, I claimed it went in the clockwise direction. Clockwise. It is a circle centered at the origin of radius 1. It's a little teeny tiny circle. Fine. There it is. So what do I notice about the shape? Circle. What range of time do we sketch out only once? I claim 0 to 2 pi. Now, if you don't believe me, you could always go back and change it up some. So what do I mean? Like, what if I change my window from 0 to pi? Would I see something different? Let's just check it out. Graph it. Oh, I only get half a circle. Bummer. Now, if you overshoot the mark, like if you went 0 to 4 pi, you wouldn't notice it because it'll just wrap around itself once around, so you won't know that. And so the trick is you only want to have to traverse the curve one time. It's not good to double wrap around. So this one, 0 to 2 pi, is sufficient. Okay, so 0 to 2 pi, and then how do we eliminate the parameter? This one you don't solve for t. It's not going to work. You'll end up with arc sine or arc cos, and you'll get a hot mess. So here's the trick. Anytime I have sines and cosines in my parametric equations, I try to figure out if I can use this trig identity, sine squared, plus cos squared. Whoa, what am I doing here? Cos squared equals 1. So can I use that trig identity somewhere here? I hope so. And so what I do is I take my x, which is sine, so I can go x because it's sine t, square it. Cosine is y, square it, and then I get 1. So x squared plus y squared equals 1 is the single rectangular equation. And sure enough, it does match the graph. So that is eliminating the parameter with trig. And we'll do a couple more of those so you can really see what's going on there. I actually am showing you my Calc 3 lecture right here. Because when I do Calc 3, we do a review of parametric because you need it. Okay, so what if they said, hey, sketch this curve. This is parametric equations. Here, theta is the parameter. Well, how come theta is the parameter? That messes, I like t. Yeah, but I don't want you to get addicted to any one parameter. They may use t as the parameter. The next moment, they're going to use theta. The next moment, maybe they'll use m. I've seen s as in Sam used, and you'll see that in Calc 3. So you'll see different parameters. So, well, how am I going to graph it now? Don't worry. When you do your graphing calculator, anytime they use some other variable, it's a dummy variable. Just keep using t because that's what our calculator has. Don't sweat it. So the x here is 2 cos, and they said theta, but t. And then the y is 5 sine t. And then you hit, let me check my window. I think 0 to 2 pi. Let's do 2 pi to be the max. I don't want to contribute to global warming here and make the computer work harder than it has to. Oh, I want 2 pi. Stop. 2 pi. 2 pi. Come on, baby. I can't see where my pi is. Nope, I don't want E. Try again. My poor eyeballs. Okay, now hit graph. Oh, whoa, that was cool. Looked like a counterclockwise ellipse. Nice. Okay, put that in there. It's an ellipse, and if you check it a little bit closer, 5 and negative 5 are the y-intercepts, and 2 and negative 2. There it is. It's an ellipse. Very nice. You guys get that? I hope so.
Yes.
Roman, a quick question. If you're not drawing the graph, may I suggest that you go to mode and make sure you're in radians mode. See where it says radians, not degree? You may be accidentally here in degrees mode and you just forgot. When you're trying to graph trig, I know it's very annoying, but you have to make sure you're in radians mode and then hit enter to make sure you choose radians and then quit out of here and then try it. It should fix it. Let me know if that fixed it or not. Can you try it now? Did that fix it? Fingers crossed. Ah, okay. Thank you, God. All right. What were our Windows settings? 0 for the minimum and 2 pi for the maximum, Jasmine. 0 to 2 pi is the window. Yeah, should work. I mean, you could do 0 to 4 pi, but it'll wrap around your ellipse twice. You won't be able to see that, but it will. Okay, is everybody else working it? Having fun? See, isn't this better than finding the radius and interval of convergence? Yes, no? I don't know. Okay. How do we eliminate the parameter? Well, I still claim we're going to use cos squared theta plus sine squared theta equals 1. That's the trig identity that will help us eliminate the parameters. So then what? Here, solve for cos. Well, that's easy. Cos theta is equal to x over 2. Okay. And then here, you're going to solve for sine theta, and I get sine theta equals y over 5. So what? Well, for cos, you'll put x over 2, and then that gets squared. And then sine is y over 5. And you're pretty much done, but if you clean this up a little bit, I think you will recognize this from your pre-calc class. This is the standard equation for an ellipse centered at the origin. Yeah? Does that look recognizable to you from the past, maybe? I hope.
It's the equation.
Yeah.
Oh no, never mind.
You got it? Okay, we're going to do another one just because, you know, more is better. So new curve, 2 plus cos theta is the x equation, and 3 minus 4 sine is the y. Okay, fine. Go back to here. Clear these babies out by hitting your clear key. Okay, so x, 2 plus cos t. Y, 3 minus 4 sine t. I'm not using the closed parentheses because I don't need to. It'll still work. I'm going to keep my window 0 to 2 pi. Watch closely. Oh, it's an ellipse, but it's not centered at the origin. Oh, bummer, man. I think it was sketched out in the clockwise direction. So the question is like, you know, it's like, you know, like that. What is the center? Well, hang on a minute. If I solve for cos, I get cos is x minus 2. And if I solve for sine, I get 3 minus y over 4. That's kind of crappy. And then I'm going to use this identity, cos squared plus sine squared theta equals 1. And in place of cos, I'll put x minus 2. In place of sine, this horrible quotient, 3 minus y over 4. Getting squared, and then what? That's, you're done. But if you want to clean this up a little bit, I claim that this is the same as y minus 3 squared over 16 equals 1. And you can kind of see this is the equation of an ellipse where it's centered somewhere else. Where's the center point? And I claim the center is 2, 3. If you learn that from pre-calc. So if you locate the 2, 3 right there, there's your center point. And x and y are not intercepts, but if you go to the left and to the right 1 unit, that's your minor diagonal. And then the square root of 16 is 4. So go up 4 units and down 4 units. And you'll get this ellipse here, like that. All right? Not centered at the origin. Okay. And this is the single rectangular equation that matches the parametric equations. And it's an ellipse. Another one. Okay, now we're going to get a little bit harder. So watch yourself here. Well, what's so hard about x equals square root of t and y equals 3 minus t? Nothing is hard about that. The hard part is going to be giving the appropriate rectangular equation, because we may need to restrict the domain so that the curves match. What the heck am I saying? Well, first, go to your graphing calculator. Graph this baby. Y equals clear, clear. Okay, x is square root. Oh boy, square root of t. Fine. Y is 3 minus t. Fine. Now, I could have the window change where t minimum is negative and like -10 to +10. You can, you go ahead and try it. But it turns out because you're taking the square root of time, you don't want to take square roots of negative numbers. Your calculator will actually let you, it'll just ignore you. It won't give you an error, but that's not good. You want to stay away from the world of complex numbers in this class. Other classes, it's cool. So we're going to keep our t minimum at 0, and you can keep your t max at 2 pi or make it to 10. I don't care. Well, I'll do 10 just for fun. Hit graph. Oh, that went too quick. I didn't even see it. Gosh darn it. I claim it went whooshing down. So the orientation, you want to note that on your paper. It did whoosh downward like this. All right. Like that. Now, how do you find an x-intercept? You want to guess? What do you know about x-intercepts? The y-coordinate is 0, right? So then what? If you set y equal to 0, the time that you get is 3 seconds. It's 3 seconds when y is 0. Plug 3 seconds into the x equation and you get x equals square root of 3. So this x-intercept has coordinates square root of 3, 0. That's how you get it. Now, what about the single rectangular equation? How do you kill off the parameter? And this is where it gets a little bit weird. So again, I write down the two equations just so I can look at them. And then I go, okay, which one of these looks like the easiest to solve for t? And they're both pretty much equivalent in difficulty of solving for t. But how about if I choose the x? So I'll solve for t by squaring both sides. Fine. Then what? Substitute this in place of the t into the y equation. So I get y equals 3 minus x squared. Now, you think you'd be done, but here's the problem. If you graph this rectangular equation, I'll do it on a different graph over here, you'll get a parabola. Okay, so what's wrong with that? Well, what's wrong with it is that you want this graph to match this graph over here. And right now they don't. Here you get the full enchilada here, you know, the full parabola. Yeah. Over here, I only get half of one. Oh man, how do I make a match? I know, I'll just erase half of it over here. You know, I'll erase this left half. Yeah, well, yeah, you could erase it, but what are you really doing? You're restricting the domain. You're basically saying, hey, y equals 3 minus x squared. I'm not going to let you have your left half of your parabola. And how am I going to do that? I'm going to restrict your domain so that x is always greater than or equal to 0. And that way I'll only get the right-hand side of your parabola. And I'm done. So this is the full answer to eliminating the parameter. You need to add this little extra thing about x. If you don't, then it's not correct. Okay, I know that seems like a tedious detail, and I won't argue the point, but that's how you roll. Okay? Questions at this point? Okay. So let's just do one more weird one. This is a weird example. Weird. Just, I love the weirdness of it. Okay. You're not going to see this in Briggs. Okay. But it's cool beans. The idea of it you may need. They're the parametric equations. Okay, let's go graph them. Hey, go to the y equals, clear button, fine. My x equation is t squared minus 2. My y equation is 2 minus t squared. My window, I am going to want my window to do anything and everything. So you can, you know, try your window -10 minimum and time maximum 10 seconds. So when you graph it, it's a portion of a line. So here's the weird part. What was the orientation? It went by pretty quick, and you may think that you know it, and that's going to be your first mistake.
Did it go up?
It did, but it also went down.
Oh.
That's what's so annoying. Well, how do you know? Well, because I'll show you what I mean. If you restrict your time from -10 seconds to 0 seconds only, what you're going to notice is it goes to the left and up. But then if you go back into your window and have t minimum be 0 seconds and t maximum be +10, when you hit graph, watch, don't blink. You blanked. It actually went down. So what the heck? And then it stops, like it doesn't even go. It has this little, it makes a U-turn right there at that one point and turns around. What the heck is that one point? So when you graph this, you're going to actually have to put 2 arrows here, one going up and one going down, because you have to represent it went whoosh, and then it made a U-turn and whoosh, went back down. That's nuts, isn't it? I love that. That's just so nerdy. You should all be saying wow right now. I'm not kidding you. Wow. 2 arrows. So how do you eliminate the parameter? Now you could solve for t and you'll get a square root and it'll be a hot mess. So here's the easy thing I want you to notice. Notice that t squared is in both equations. And I'm going to use that to my advantage. What do you mean? For the x equation, I'm just going to solve it not for t. Let's just solve it for t squared, not t. You'll see what I mean. I'll make it easier for you. So t squared is x plus 2. Fine. Then what? Substitute this into the y equation now. You know that y is equal to 2 minus t squared. So you'll replace the t squared, and don't forget parentheses matter here, with, because you're going to have to distribute the minus, with x plus 2, like that. And then distribute the negative, and I get y equals 2 minus x minus 2, but then the 2's cancel, hey, hey, and then you get y equals -x. But here's a problem. That's not the final answer. Why not? Because if you graph y equals -x, you know, this is like an algebra problem, you're going to get this diagonal line. Well, what's wrong with that? Nothing's wrong with that, except we need this curve to match this curve over here. And right now they don't, because this diagonal line doesn't have a cutoff point. So what you're going to do is you're going to restrict the domain. I want it to cut off at this point. Now, how do I know what this point is? I claim this is when time t equals 0. And if you plug t equals 0 into the x and y parametric equations, you'll get the point -2, 2. So you want a cutoff here. So you only want the y equals -x up to the point -2, 2. So you'll restrict the domain. X has to be greater than or equal to -2. And now this is your answer to restricting the, eliminating the parameter. You needed to restrict the domain. Okay, a little bit advanced, but I think you can handle it. You can. I know you can. You've come this far. If you made it this far, this is easy compared to some of the stuff we've done this whole semester. Like, for reals. We've done some crazy stuff, people. You'll remember it forever. Okay, let's do a little bit extra. And then I might even have you try one. All right. We'll cook one up for you. Yeah. Okay. We're going to convert between rectangular and parametric. So you need to know how to do this in Calc 3. We've already went one direction. We went from parametric to rectangular. Well, what do you mean? We did that? Yeah, we did that all on this page here. When they say eliminate the parameter, which we did a whole bunch of times here, you are going from the world of parametric to the world of rectangular. Okay. Well, what if somebody said, I want you to go the opposite direction? You got to go both ways, baby. Well, what are you saying? I'm saying if I give you a single rectangular equation, give me a set of parametric equations that graph the same thing. And I'm going to teach you the Rasky school of foolproof. You'll never blow this if you follow my lead. Okay? Here you go. The Rasky school here. Rasky school of converting from rectangular. You want to go from rectangular to parametric. Okay, so number one, ask yourself, is it a function of x? like, in other words, you can rewrite it as y equals f of x. Good. Then let x equal t, and y will be whatever that function was, but replace all the x's with t, and you're done. That will be the answer. The second thing that could happen, if it's not a function of x, ask yourself, is it a function of y instead? Now, functions of y are written in the following format. X is equal to some junk that has y's in it. So it'll look like x equals g of y. So how do you parameterize? That's a word. Parameterize that. Here, you're going to let y equal t instead. Before you let x equal t. Here you let y be t. And since x is equal to some function of y, x will be whatever that function is of t. And then finally, what if it's neither a function of x or y? Well, what do you mean? Like, well, am I screwed? Like circles are neither a function of x or y. So what it just as an example, like x squared plus y squared is equal to 4. That's, a circle doesn't pass the vertical line test. So it's not a function of x and it's not a function of y. Then try using trig identities. Trig identities, like the Pythagorean one, sine squared plus cos squared, and then the other one, tangent squared plus 1 equals sec squared. That could help you also. One of those two should help you. Okay? Otherwise, that's the time to start crying. That's what I do. If my trig identities don't work, then time for tears. Okay? I'm not going to give you something that doesn't have one of these 3 rules apply. So you'll be safe. Don't worry. And same goes for Calc 3. Okay. So example 7, now you're ready. Is that a function of x, a function of y, or neither? What do you think? Come on, it's obvious. Function of what?
Function of x.
Yeah, function of x. So what do? Let x be t, and then y to us be 2 over t minus 1. And you're done. It's that easy. Now, if you wanted to prove it to yourself, like, I don't believe you. Okay. Well, then what I would do is you go to your graphing calculator. We're already in parametric mode, so we might as well just go ahead and graph the parametric equations we just are thinking it is. X equals t, and then y is equal to 2 divided by parentheses t minus 1. And I'll have my window going from -10 to +10 just to capture the whole picture. Make sure, I usually try to do that. It's my usual go-to window. Graph it. Whoa, it's got 2 branches because it's got a big old vertical asymptote there when x, or in this case, t is 1. Okay, so there's that. Now, to go back to func mode, remember, if you are going to go back to func mode, hit mode, go back to function, hit enter. So now you're back in function mode. Oh boy, this is where it's boring. And then you go back to y equals x. Oh, don't look at those. What were we doing? Oh my goodness. And then y is equal to 2 divided by parentheses x minus 1. Let's see if this curve or graph matches the parametric equations one. It should. Yep. Doesn't have that asymptote thing showing though. Okay. So it's a match. So we're safe. We did good. And that's it, basically. That's called parameterizing. And it's not that hard to do. So let's take a look at another example. You're going to love this. I'm serious. What if you had a vertical line? You guys know vertical lines because they talk about this in pre-calc and calc. And you know how to graph this because you already know about vertical lines. Now, how do you get your graphing calculator to graph vertical lines? Well, you can't because they're functions of y, not functions of x. So you can never get your graphing calculator to graph a vertical line. But now you can. So what are you going to do? Since you have x equals, and I already told you when you have x equals, let y be t, and then x is equal to whatever it is. In this case, x equals 4. So go back and I'm done. Really? Yeah. Well, go prove it to yourself. You don't believe me? I've now given you the keys to the universe there. You now can graph vertical lines. Should be so exciting. You got to go in parametric mode though. We got to get back to parametric mode. Let me go back to parametric, hit enter. Whoop, doo, doo, doo. Y equals, let me clear. Okay, x is 4 and y is t. And I want to make sure I'm negative 10 to 10. Yep, I got the whole picture. Hit it. Whoa, did you see that? Yeah. You just graphed a vertical line on your graphing calculator, and that'll work every time. Anytime you want to graph vertical lines now, or functions of y for that matter. Anytime. Like, you know, in pre-calc, they'll give you like x equals, I'm just making something up right now, you know, y squared minus 2, for example. And you'd always go, oh man, I know that's a horizontal parabola, but, you know, like this one right here. I can't do it because I'll just have to use my knowledge of graphing horizontal parabolas. Oh, God. Now, no problem. You're going to go, let y be t, and x is t squared minus 4. And boom, you can graph it now. Prove it. Go back here to my graphing calculator. Let's clear these babies out. And so if you're going to graph x equals y squared minus 4, x equals t squared minus 4, and y is just simply t, and then hit graph, and boom, there's your horizontal parabola. Isn't that great? Exciting. You'll never be stuck again. You now have the tools. You should be like so happy now. I don't know. I don't feel the energy. I'll check the chat. Nope. Why did mine only show half? Oh, okay. I'll tell you why, Clayton. Your window. If you only got half of the horizontal parabola or half of your vertical line, go in a window and make sure that your t minimum is negative 10 seconds and your t maximum is positive 10 seconds. Get the whole picture, negative 10 to positive 10, and it should fix the problem. Did it, Clayton? I hope. Did you get the full picture?
Yes, thank you.
Okay, yeah. All right, that should fix it. Now, what about this? This is a circle, and so it is neither a function of x or y. Oh boy, now what? Well, you can't use the, you know, let x be t or y be t thing. So you're like, now what? Well, now you got to use a trig identity. Okay, so what you're going to do is, you know, you're going to use cos squared plus sine squared equals 1, or sine squared plus cos squared. I don't care the order, okay? Like, don't go, oh, well, it matters the order. No, it doesn't matter. Just pick one. I don't care. Okay, fine. Now what? You first need to get a 1 on this right-hand side. You need the 16 to be a 1, not a 16. Because look, you're using this trig identity here. And I hope you see that you need a 1 over here, not a 16. So no problem. I'll just divide both sides of this equation by 16 and then kind of clean it up a little bit. Okay. Like this. Okay, then what? Now, this is the part I try to get it to look like this trig identity, you know, something squared plus something squared equals 1, like that. Well, x squared over 16 can be rewritten as x over 4, that quotient squared, and then the y squared over 16 is y over 4. Now, why is that important? Because what you're doing is you're comparing these two equations, and you want them to be looking similar, and this is the part where you make the leap. You go, well, x over 4 has to be equal to cos theta, and then solve this for x. So x is 4 cos theta. And remember, theta or t, doesn't matter what the dummy parameter is. And then you do a similar thing. Y over 4 is the sine theta getting squared. And when you solve this for y, you get y equals 4 sine theta. And you're done parameterizing. You can use theta or t as your parameter. And if you want to prove to yourself that this really is going to be a circle of radius 4 centered at the origin, heck, you know, go here in your parametric mode, which we already are, and you're going to go, okay, you know, 4 cos t, 4 sine t, and graph it, and boom, there's your circle. So it works. Yay. Mhm. Now, when you have parametric equations, you can get some pretty cool curves. I mean, just you have access now to all kinds of weirdness. and this one is really kind of fun. Check this out. You have a set of parametric equations, x and y, and they're asking you to have your interval between 0 and 4 pi. And then they're going to ask what values is this function not differentiable. You guys remember some Calc 1. Let's see if you do. Your Calc 1 grads, hopefully this will click once you see it. So first I'm going to go over here to graphing calculator. Clear, clear. Okay, my x is theta minus sine theta, but I'm going to use t minus sine t. And then the y is 1 minus cos, fine. Now they did tell me they want the range to go from 0 to 4 pi. So let's honor their request and hit it. Let's see this fun graph. Watch this. Whoa! That looks like a roller coaster. I don't know. I'd rather do a window where I go negative 4 pi to 4 pi. Let's see that. Oh, there's more. See, that's more fun. So where do you think the function is not differentiable? If somebody was talking about derivatives here. Do you guys remember that you can't differentiate at certain spots on a curve? Anybody remember like where this?
Yeah, at the origin or the beaks.
One place, yep. Where else?
Where there's like a shift, so at like those little V looking spots.
These little sharp corners.
At the cusp.
Yeah, cusps. Yeah, cusps. Yeah, special name, cusps. So those are at the cusps. It's not differentiable. So where are those values? What is theta and what are the coordinates of the point? And remember that we have a lot going on here. You know, you've got like doing, you know, like this. So at these cusps, these sharp corners, you can't differentiate. So what's going on? And it looks like at the x-intercepts. So how do you get an x-intercept? Like, you know, I want to know the exact coordinates of these x-intercepts. Even one of them would be nice. So what you do is you notice it is at the x-intercepts. And so that's when y equals 0. So force y to be equal to 0. So here's y. And basically substitute a 0 in place of the y. And then solve this for theta. Now remember, theta could be t. I personally prefer t, not theta, as my parameter because I do like to think of it as time in the little storyline. But here we have theta. And if I take cos inverse of both sides of this trig equation, I'll get, and remember, there's always other answers that are coterminal. What are angles that have a cosine value of 1? I think 0, 2 pi, 4 pi, negative 2 pi, negative 4 pi, etc. Goes on forever. There's infinity places because this curve goes on, you know, in both directions infinity times, and you've got infinity problem spots. But the question is that doesn't give us the actual value of the point. That just gives you what theta is doing, or as I like to say it's time. These are what time it is. Like you looked at your watch, oh, at 0 seconds, which is right here, I got a cusp. Oh, at 2 pi seconds, I got another cusp. It doesn't give me, those aren't the x-intercepts itself. So how do you get the actual x-intercepts? Well, we know the y-intercepts are where these occur. So each of these x-intercepts have a y coordinate of 0. But if you substitute, let's just say theta equals 0 into your x, and x is theta minus sine theta, you'll get 0 minus sine 0, but that's 0. So we know that this point 0, 0 is one of the spots, but how about that one right there? How about substituting 2 pi? So x is equal to 2 pi minus sine of 2 pi. Ah, since sine of 2 pi is 0, this is going to be the x coordinate. So right there, it's going to be 2 pi 0, and then and so on and so on. So you'll get access to where the locations of those cusps are. Okay. Any questions so far? Okay, I want to give you guys one. So I'm going to find, I'm going to put you in a breakout room. So I'm going to grab Briggs here. See, right off my shelf. There it is. And then we're going to, let's see if there's something fun in here for you to do that you can use your graphing calculator. Yay. Yeah. Oh, I don't want to give you something too messed up, but let's see here. Does it ask you to? Oh, yeah, it does. All right, I'm going to give you 2 problems, one to parameterize and one to eliminate the parameter. How's that? Okay, so this is not in your course reader. This is just for you to go do something fun here. So if I get a page going here, let's pen a page. Okay, so you and a buddy, you're going to do 2 problems. I want you to go back and forth between rectangular and parametric. That's my plan for you. Okay, so first up, so let's say here's parametric equations, param equations. So how about x equals 3 plus t and y equals 1 minus t? Okay, you're gonna, so I want you to graph this. And then, so this is part A, this will be 1. And then part B, eliminate the parameter. And what does that mean? That means come up with a single rectangular equation that involves x's and y's only, whose graph matches the graph you got when you graph the parametric equations. Okay, part 2 is, how about if I give you a rectangular equation and say, okay, you need to parameterize it. And so that's not as, let's see if they make you do that. Well, you know, yeah, here we go. All right, so how about given the rectangular equation, let's get a good one here. Oh, how about x equals y cubed minus 3y? Come up with a set of parametric equations that go with this equation. Okay, so you got to go back the other direction. Okay, so if you're confused, don't worry, I'll come around to your breakout room and you can ask questions if you're stuck. But meanwhile, have your graphing calculator handy because you'll need it. It's fun. Okay, so I'm going to put you in to breakout rooms right now for a little bit of fun and play of what we just learned. And go for it. Turn on your mics. Talk to your buddy. Good luck. Good luck. Mm-hmm. Mm-hmm. Okay, guys, how'd we do? Do you feel pretty comfortable? Yes, no, maybe?
A bit more.
Okay. So I'm hoping that you whipped out the calculator and you graphed the set of parametric equations that were given. And to be honest, I don't really know what the answer is because I just, pulled these up myself. I just kind of pulled them out of the book. So what do I have? 3 plus t, 1 minus t. Okay. So 3 plus t, 1 minus t, and check my window. Negative 12 to 12 is good. I'm good. And hit it. Whoa, okay, it's a diagonal line. Fantastic. Nice. Okay, and it looks like it was going down. And it looks like the x and y intercepts are 4s. Okay, lovely. So, here's my graph, 4s. And put an arrow. So it's going down. Now what? Eliminate the parameter. Oh boy. So we have to come up with a single rectangular equation that's the same graph. So it's kind of up to you. Which one of these do you want to solve for t? You can pick one, whichever's the easier in your mind. They're both about the same. So how about if I just use the x equation? So when I solve for t by subtracting 3 from both sides, and then substitute this into the y equation. But y is equal to 1 minus t. So when you plug in the x minus 3 for t, be careful because you will have to distribute the negative. So you'll get 1 minus x minus a minus. That'll be plus 3, but that's just 4 minus x. And you're done. And you can prove that this graph matches the same. Now, some of you solved it for x instead. That's fine. You would have got x equals 4 minus y. That's just as legit. You do not need to restrict the domain. This graph is the very same graph as this graph up here. You don't have to cut it down or anything like that to make it match. So you're done. Any questions on number 1? Eliminating the parameter, going from the parametric equation world to the rectangular world. Not too hard, right? How do you go in the reverse direction? Somebody gives you a rectangular, you have to do the parametric equations. Now, if your pre-calc instructor said, hey, go graph x equals y cubed minus 3y, your graphing calculator only likes functions of x. This is a function of y. So it's like, well, you could just graph it by hand, and that would take you a long time of plotting a whole bunch of points. Ugh. So how about instead parameterizing it? Yeah. And functions of y, I already gave you the Rasky procedure up here. Remember, if it's a function of y, you let y equal t, and then x equals whatever, but you plug in t's in places of y's. Okay, fine. So function of y, you're going to let y be t, and then x is t cubed minus 3t, and you're done. You parameterized it. And just for fun, let's see what the graph of that looks like. Because, now you can actually graph functions of y. And that's the really fun part of learning parametric, in my opinion. So you're going to have x is equal to t cubed. Oh, sorry. For some reason I was at the y. Okay, y equals t. There we go. And then x was t cubed minus 3t. And let's check my window. Negative 12 to positive 12 looks good. Hit it. Whoa! That's nuts. Isn't that pretty? I don't know. I like it. Wow. It kind of looks like an S, like whoosh, like that. Fun. Okay. Any questions on this? So this is parameterizing. Everybody okay? You got it?
Yep.
Okay. To finish up, I'm going to do a little bit of calculus and then I'll let you go. Oh man, no. Yeah. You got to have, look, today's lecture, seriously, we didn't even need more than half a brain cell. It was just all fun and games with parametric equations and graphing and, eliminating parameters. Maybe a couple brain cells when we had to use the trig identity. Fine. But no calculus. That's not fair. So how would you find slope of curves? Because, with this S curve here, that's awesome. What if somebody picked a point like right there and said, hey, I'm going to draw a tangent line to that curve. Here's a tangent line. Not very good, but whatever. Hey, go get me the equation of that tangent line. Oh man, we used to do that in Calc 1. Yeah, I know. A lot. I get it. But here's the thing. You're going to be asked to do it now again. So get used to it. So we're almost like going back to Calc 1, but we're going back to Calc 1 in the world of parametric. And that's pretty much what we're doing, like for reals. So we're going to do parametric. And so today I just want to do the slope equation. It's super easy, you'll see. Super easy. And then we'll do more weird calculus next time because it gets worse. You got to know your arc length. And what? We already did arc length this year. I know, but we're going to do more. I know. Okay, so calculus and parametric equations. So what are you going to do? Calculus and parametric equations. You're in a calculus class, people. Come on. So we're going to look at slope and arc length. Those are the two big calculus ideas. I'd like to start it today because on Friday, if possible, some of you may want to do a quickie review of 11.3 and 11.4. I don't know, maybe. I just had somebody tell me that they're stuck on 11.3, 11.4. That was last week's material because they totally didn't remember anything we did last week because you were too busy getting ready for the exam this week. I get it. And we can go over some of that last week's stuff too in my special office hour for you. I'd be happy to do a quickie review of last week's junk. Come on down. Okay. So in Calc 1, you know that if somebody asked you for the equation of a tangent line, you would go, no problem. I just go get f prime. And that'll be the slope of my tangent line. And, you know, go get dy dx, essentially. Same thing. Well, now that we have parametric equations and we have that extra variable thrown in the mix, the time, I like to think of my parameter t as time. Time got introduced into the story. How do you get dy dx? Well, you could always just immediately convert to rectangular and do dy dx in the world of rectangular, but that might be a little bit tricky. So better to just get the straight on formula for the derivative. And this is called the parametric form of the derivative. So your dy dx can easily be found if somebody gives you a set of parametric equations that looks like f of t and g of t. You take the derivative of the y equation with respect to t and put it up top. And then you divide by the derivative of the x equation with respect to t and put that on the bottom. Please be careful because a common error, including your instructor, I've done this more times than I should admit to you. I'll admit you all my silly errors. I've accidentally screwed this up too, where you accidentally switch who goes on top and who goes on bottom. That's super common error because normally we like to think of x as going on top and y is on bottom. But you kind of want to think of this as slope where you're going change of y over change of x. So you want the dy dt to be in the numerator, not the denominator. Don't blow this because you'll get really mad at yourself if you do this silly mistake. Okay, I've done it and I get really annoyed. So let's just do one quickie example and then we're out of here. Okay. Okay. So here's a set of parametric equations. Fine. Now, just for fun, I like to see what it looks like. Hey, x equals t squared, you know, you don't have to graph it every time, but you know, if they don't ask you to, you don't have to, sure. But I always like to look like, hey, x equals t squared and y is 3t minus 5. And my window, yeah, my window's fine. Okay, hit it. Oh boy. And if I zoom out a little bit, it does look like a parabola, sort of. Yeah, it's a sideways parabola, fine. And then when t is equal to, time equals 2 seconds, I don't know where that would be, I'd have to find out. They want to know what the slope is of this lovely parabola, fine. Okay, now time t equals 2, I'm just curious, they don't ask me this, but what's the location on that parabola? If you plug in 2 into your parametric equations, you'll actually find the xy coordinates of the point that they're trying to find the slope of. So if you look at this curve here at the point 4, 1 is where they're trying to figure out the slope. looks like it's going to be a positive number, but hard to tell. All right, so what is the slope? So you're going to go slope, which we call dy dx, is dy dt divided by dx dt. So we're going to do this on the fly. So the derivative of 3t minus 5 with respect to t is 3. Divide that by the derivative of the x equation with respect to t. Derivative of t squared is 2t. I'm done. There's dy dx. You're going to evaluate at time t equals 2 seconds. And the notation, because I want you to notice this notation, they'll put a vertical bar, and at the bottom of the vertical bar in subscript notation, they'll put the time that you want it evaluated at. And this is just substitution. So you'll just plug in time t equals 2 seconds, and I get 3/4. And so the slope at this point for 1 is 3/4. Okay, and we're done with letter A. And letter B is going to be a little bit trickier because they didn't give you a time. They're giving you the point. Uh-oh. So at the point, so you've got that, you know, sideways parabola. At the point 9,4, say right here, you know, if I drew a tangent line at that point, I'm not very good at drawing straight lines, so forgive me. Yeah, that looks pretty great. Oh, okay, whatever. What's the slope, which is dy dx, of that pink line? I don't know. The problem is I have my dy dx. It's 3/2t, but I need the time. So letter B, I'm a little bit stuck. I need time t at the position 9,4. And don't go, oh, it's 9. I just, it annoys me when students go, oh, I'll just take one of the x or y coordinates and I'll use that for my time. No, no. Now you might get real lucky on occasion, and that might be the case, but So here's the way you do it. What they're telling you is at some time, x, which is t squared, has to be 9. At the same time, the y, which is 3t minus 5, that y coordinate they're telling me is 4. So what value of time t satisfies both of these equations at the same time? Now, when I solve this for t, for the x equation, I get 2 possible answers. Uh-oh. But when I solve the other y coordinate equation for t, add 5 to both sides, I only get 1 answer. So you pick the one that makes both of them at the same time. So we're going to go with t equals 3 seconds. And that's the time that you will substitute into your slope. So you're going to evaluate dy dx at the time 3 seconds, because 3 seconds is when the position is 9,4. And that's easy because you'll have 3/2 times 3, which is 1/2, and you're done. So that would be the slope at that other point. And we're done. Now you know how to find slopes of curves that are represented by parametric equations. So congratulations. And yes, this is easier than power series, okay? I will agree with you.